In Chapter 2.1, we're going to start talking about some rates of change and lead up to the concept of limits, which is a very important concept in calculus. If you'll see here in the notes, I have written about something called average speed. Average speed traveled over a distance is found by dividing the distance traveled by the time it took to travel it. Now that may sound kind of abstract, but if you think about it, you do this all the time. I went to Indianapolis. It took me 2 hours. It's 70 miles, so I drove an average of 35 miles per hour. We all know that when we got on I-70 that we drove probably 70 or more. So the average of 35 miles per hour, there are places where we went slower, we went faster, so we didn't leave our driveway going 35 miles per hour and stay at 35 miles per hour the entire time that we took. So we have an average time, and this works well for us in most cases. Now the book leads into this concept of the distance caused by gravity, which you may have seen before in physics. So if you took a regular solid object like a rock and you dropped it from a free fall, you didn't give it any push, notwithstanding air resistance, all of that, the distance that it will fall is y equals 16t squared in feet. In other words, if I plug in the time, the distance that the object falls is given to me by y. So in the notes here I said an object dropped from rest in free fall to the surface of the earth will fall y equals 16t squared feet in the first t seconds. These things will connect here shortly. So let's move on and let's talk about this particular rock. So in order to find the average speed of a rock being dropped at rest, we take the distance traveled that we call delta y. Recall that in the beginning of the class we talked about delta y being the change in y, divided by the interval delta t, which is the change in time. So in this particular case, we took that formula 16 equals y equals 16t squared, and we plugged in the value of the time. As you can see here on the screen, the end time is first, of course, minus the start time. And so this is the distance. So we take that y equals 16t squared, we get the distance, and we divide it by the time it took. Once you plug those in, you get 64 divided by 2 equals 32 feet per second. So a rock will fall at an average speed of 32 feet per second in 2 seconds. And I rewrite this here. Therefore, an object such as a rock will have an average speed of 32 feet per second. In other words, in the first 2 seconds, it will have fallen 64 feet. So if we continue with this thought, then we go into the instantaneous speed. Instantaneous speed is an exact speed at a given time. Like I said earlier, when we leave our driveways to go to Indianapolis, we don't take off at 70 miles an hour. We tend to speed up, slow down, stop for red lights, stop for traffic, and that affects the average speed. So the speed that I'm going at exactly 2 seconds is not going to be the same speed I'm going at exactly 4 seconds, and so on. So let's look at this from a different viewpoint. The instantaneous speed is the speed at any given point in time. So if we want to find the speed of the following rock or object or whatever in the previous example at exactly 2 seconds, what we need to do is set up t equals 2. The time is 2, and we use this variable h to express an increment or a small amount. You will see this used over and over, and that's what it means, just a small amount. We're going to just increment a little bit. So at t equals 2, a slightly later time can be expressed as t equals 2 plus h. Using the same formula that we did for average speed, we're going to plug in the 2 plus h and the 2. So essentially what we're saying here is the change in distance can be found by 16 times 2 plus just a little bit more time minus 16 2 squared at exactly 2. And we divide that by some very small increment of time. And this is going to lead us into our concept of limit, because when we're looking at the small increment of time, we're trying to get this as small as possible. In fact, we want to get it as close to 0 as we possibly can. because that's what we're looking at is the exact moment. However, if you'll notice, we can't evaluate this particular formula when h is 0 because we can't divide by 0. However, we can get an understanding by evaluating this formula for values very close to 0. So your first example to complete is this formula on this page for delta y over delta t equals 16 times 2 plus h squared minus 16 times 2 squared all over h. Notice in the table I've put smaller and smaller and smaller values of h. I want you to input those into the formula for delta y over delta t and write out your output. Please use a calculator. It's going to be a lot easier on you. And tell me what you're getting very, very, very close to. This will be one of the things I collect and check that you did on your when we come back into class. All right.